it's a feature extraction technique. In this, the data is being transformed from the one space to the other space, and the new set of features I am talking about y1 or y2 is a linear combination of original features. Okay, it's a linear feature extraction technique. Okay, six, the projection that preserves as much as information in the what is called data. So as I already discussed, the PCA will try to minimize the information loss. Let's try to minimize the information loss, right? As we already discussed this point. And LDA, so as I mentioned, is the try to maximize the class CDA, class discriminatory CDA is class discriminatory information. Now let's see if you want to understand the principal component analysis or LDA, linear discriminant analysis. Some preliminaries are required related to vector algebra. So how the data sample is represented in a vector and how we can find the projection of a point in some direction of the. So how we can find the projection in the vectors and all. So this is my a vector, a sample. A sample can be represented in the n-dimensional space as x1 comma x2 comma xn, means there is a point and there is x1, so x2, and there is a xn. It means there are n components. This is called a component. It is also called component. There are, means any feature is having n component, means this feature, this data is having n dimensions. So if you take in two dimensions, if you are simply taking two dimensions, the two dimensions, there is x and there is a y. If a point is there 2 comma 3, 2 comma 3, let it be I comma j, so I comma j for simplicity. This is called x, okay? So I comma j and this is called x. X is equal to 2 comma 3. So what is meant by 2 and what is meant by 3? So 2 is nothing but value but 3. If I want to reach 2 comma 3, this point, I have to walk 2 units in the x direction and then I have to walk 3 units in the y direction to reach this point. It means that. So what is this x and y? What is 2 comma 3? So 2 comma 3 is the components of the vector x. The 2 comma 3 is a vector, but what component? So 2 comma 3, it's called this 2 is a how the 2 is a the projection of point 2 comma 3 in x direction. What is mean by t? What is the 2 means? How can I interpret 2 means? 2 is a projection of point x 2 comma 3 x 2 comma 3 in x direction, x axis direction. So this is called not I, in I direction. So what is the 3? The 3 is a projection of point x 2 comma 3 in jth direction. Jth direction. And another important thing is I comma j are called base axis or base vectors, and the mod of I is equal to mod of j r is equal to 1, and the they are orthogonal or orthonormal. Ortho means there is existence. So I comma I is equal to 0. I dot j is equal to 1. There's a perpendicular. Now, so I comma I is equal to 1. I j is equal to 0. now. So they are orthonormal. This the size of this is mod of I and M is j, and these are called orthonormal basis vectors or base axis. The same analogy I am applying for n dimensions. So there are some n dimensions. There is a point x, and it is having x1, x2, and xn, and there are axes. Basis axis is called you can say v1, v2, v3, and v. Yeah. Means that the same analogy if I apply. So there is a point x, x1, x2, and xn, and so what are the basis vector for all these points is v1, v2, and vn. So these basis vector are common for all data samples, like x1, so this x, something like you may have some not y. So whatever is values are there, so whatever the data sample are there, this basis vectors are common to all these. This is basis vectors, like similar to I comma j, means mod of v1 is equal to mod of v2 is equal to mod of vn is equal to 1, and they are orthogonal. Means v I vi into vi is equal to 1. So vi into vj is equal to 0 when I is equal to j. Vi into vj is equal to 1. So I not equal to j, it is a 0 something. So if that is the case, now I am generalizing. I generalized it. So what is this basis vector v1, v2, v2? Then what could be the x1? How can I interpret x1? x1 is a projection of or something, this is called component or the projection component or component of the projection component of x in v1 direction. Similarly, x2 is the projection component of x in v2 direction. Same thing. So, right, now same thing I explained. Assume the standard basis vectors. So v1, v2, and vn are the basis vectors. These are unit vectors, and of course they are orthonormal. Xi can be obtained by projecting x along in the direction of vi. So x1 is a projection in the direction of v1, x2 is a projection in the direction of v2, and so on. How we will get this projection? How we can get the projection? How we can get projection? The projection of the point is given x transpose into vi. In which direction you want to get the projection? So in the vi direction. So x transpose into vi and divided by the vi transpose into vi. This is nothing. Vi transpose into vi is nothing but its a value is 1. You can 1. So this is x transpose into vi. So finally, if you want to get a transpose, you transpose x and multiply with the corresponding basis vector. So now once you have individual components, now similar this xi means you will have x1, you will have x2, you will have x3, you will have xn value, you will have some xn value, x1, so its component value, projection value, projection value, projection value. Once you have these projection values up to x1 starting from x1 to the xn, then how can we reconstruct the original point called x? Very easy, right? So from x you got x1, x2, x. Can't we get x from x1, x2, x3, xn from x to get x? Yes, definitely we can get so. So the x can be is the summation of all the components. So the summation of the components, like x1 component plus v1 into v1 plus x2 component in the direction of v2 and x3n is the component direction of vn. So this is nothing but x1 v1 plus x2 v2 plus xn vn. So this is also nothing but we can also write as x1 comma x2 comma xn. This is nothing but your x. X can be written as x1 x2 xn, and this is also can be written as x1 is the component in the direction of v1 plus x2 is the component in the direction of v2 and something like that. Since the base vectors are same for all x belongs to R2 power n. So whatever the sample which belongs to the n-dimensional space, so the basis vectors are common. Okay, so these are standard basis vector. We typically represent them as a n component vector. This is an n component vector, something like this. So this x1, x2, x3 can also write as x vector, n component vector means. So this we can write as, so this is the n component vector. It's nothing but x1 v1 plus x2 v2 and so on xn v1. Now let us take one example and then you will think understand the calculation. So let us take a two-dimensional case where the x is represented as 3 comma 4. So x is represented 3 comma 4. There is a basis vectors come I comma j and this is 3 comma 4. What is the 3? So this is a 3, this is a 4, right? That's it. So assume that standard base vectors, now vi instead of v1 I am taking I and instead of v2 I am taking j. How xi can be obtained by projecting x along the direction of vi. So what is the projection? So 3 comma 4 projection on the x-axis. The projection is the projection. Now how to get this? X transpose 2 and what is x transpose 3 comma 4? This is 3 comma 4 and into in which direction? X direction means the I, the direction is I, means here not x comma, it is ith direction, the I is, so there is a first axis, so means 1 comma 0. It is when you do the dot product you will get 3 plus 0 is 3. So similarly, if you want to get x2 component, it is which is in the y2, in the direction of y2, it is right to x transpose into j. So j is the second basis vector, so hence 0 comma 1, so you will get 0 plus 4 as a 4. Now from this x1 and x2, how can I reconstitute x? X is equal to, how can I reconstruct? This is 3 into I into 4j. X is equal to 3i plus 4j. So x can be represented as 3 comma 4. This is represented 3 comma 4. This is a n component vector. Are also represented as 3 comma 4 in the coordinate systems. The vector algebra, the vector so this is how we can construct the original vector. Uh, construct the individual components is something like this 3i plus 4j. This we can also write as 3 comma 4 or the vector form. This is the vector form. This is the coordinates form. The x can be constructed from its projections as follows. So what we have seen so far is, so if there is a vector, So what is the significance of each and every value in its coordinate system? What is the significance of the first coordinate? What is the significance of the third coordinate? They are the projections in the respective directions, the respective basis vector directions, right? Now, another important thing is they are orthonormal, I already mentioned, and they are basis vector. This is something about orthonormal because if they are perpendicular, there is a that product is 0, otherwise it's 1 because they are orthonormal. Now, the original point and is reconstructed. The x is reconstructed from the individual components x1, x2, and xn, and where x1 the significance of x1, x2, xn are they are the projections in the y1, y2, and yn respectively. When I'm summing it up, you will get the x. Or can be represented as x1, x2, and xn. It's nothing but both the representatives are same. Now come back to the PCA. What the PCA does now? Let us come. So with this preliminary knowledge, so how a sample, a data sample is represented in the vector form. So with this, now let's proceed to the PCA analysis. The PCA seeks to approximate X in a subspace of Rn using new set of features called K, which is far less than N, with a basis vectors U1, U2, UK, N, or N. So what you observe over here, very important. If you see, so what is the basis vectors of X? What is the basis vectors of X? What is the basis vector of X? V1, V2, Vn. Means if there is a point X, its basis vectors are V1, V2, and Vn. So this is coming x1, x2, and 10 because n component. Now I am transforming by using PCA. We will talk about how the PCA does to a new set of dimensions such that it is transforming to the y such that y1, y2, and yk. y1, y2, yk. And the interesting thing over here is the basis vectors are here u1, u2, k. Means the basis vectors are changing, or you can say something like new axis after rotation or some multiplication, or means the basis vectors. If the basis vectors changes, the basis vectors are changed, definitely the individual components will also change, will be changed. That's the reason the x1 is not same as a y1, x2 is not same as a y2, because the v1 are the basis vectors v1, v2, vn are transforming to the u1, u2, and uk. The base is very important. The basis vectors are changing. The basis vector, the axis are changing. The basis axis itself are changing. v1 we are transforming to the u1. So when the u1, when the v1 or v2 and vn are transforming to the u1, u2, to this new basis vectors, then this y1, y2 will be changed. Something like you are rotating the axis in one direction. Suppose if I am rotating this axis some 45 degrees, then the new basis vectors will be u1, something like u2, and something like un. Means if I am rotating certain angle, something like that. Means we are changing the basis axis. From v1 we are changing, v2 we are changing, vn we are changing. Obviously, the question is how we have to change these, change this basis vector such that minimize the data loss, isn't it? This is our objective, right? We have to minimize the data loss such that you have to change the basis vectors. That is the idea of the principal component analysis. The PCA, what we are trying to do, we are changing the base vector from u1, u2, un to the new basis vectors, namely u1, u2, uk, or un also, no problem. This is also un also, you can refer it, no issue. Un also you can say un such that the information, the data, minimize the data loss, minimize the data loss. Right. The question is, what we are trying to do here? V1, V2, Vn are changing into the U1, U2, Un. Somewhere here UK will be there. U1, U2, UK will be there. Is there any data reduction here? Dimensional reduction? Is there any dimensional reduction? No. Because here n components, here n component. Right? So our aim is in the new transformed space or in the new basis vector. So what is the subset of? These new basis vectors we should consider such that will minimize your loss. That's the reason we will always talk about U1, U2, the UK. This is a subset of this, and that will minimize the loss. So when I am transforming V1, V2, Vn to the U1, U2, Un, is there any data loss, guys? When I am changing, is there any data loss? Please think of it. I will address it at the last. Right. Yeah. The P seeks to approximate an X such that this is called X cap, such that you are transforming to a new space where the Y1, Y2, Yk are the components in the directions of U1, U2, UK. What is this U1, U2, UK? The U1, U2, UK are the new basis vectors such that when you are this data, so this, of course, this is once you know the individual components and the basis vectors, I mean the basis vector, you can reconstitute the original point. The original point I am calling, the original is X. In the new dimensional space, it is called X cap. X cap. How I am getting the X cap in the new dimensions? The new basis vectors called U1, U2, UK, and it's a components in the respective direction like Y1, Y2, Yk. Similar to the earlier. So here, what we did here, same thing. Now the question is, what is the gap between the X and X cap? If there is no data loss, X minus X cap will be 0. Okay, both will represent the same. If I find the X minus X cap, the distance between these two will be 0. So they will represent the same information, but in different form. Like something 2 comma 4 is nothing but if I multiply 2 with the 4 comma 8, both are same. Both will like something like this. Okay, so I want to minimize the gap between the X minus X cap such that what should be the K value I should consider. The way K is less than 8. So what should be the K value I have to consider to minimize this, right? So, no. Yeah, such that X minus X cap should be minimized. Means we are minimizing the information loss, data loss. Now tell me if this K is equal to, because as I said, V1, V2, Vn is transforming to the U1, U2, Un. It means both are. So is there any data loss? Please think of it. Okay, let's have some 10 minutes break and we will resume our session after 11:10. Or else shall we continue? If you are okay, I will continue for another half, then I will. Guys? Okay.
Continue, sir.
Okay. Yeah, so the question is, if I'm transforming from U1 to the V1, V to the U, so where the number of dimensions is same, U1 and but there is no change in the dimension, but only thing is values has been changed. So will there be any data loss? That is the question. So please think of, so there is no data loss here. No data loss. The answer is no. So we will. I will maybe in one of the slides I kept it. That time I will elaborate. Okay. Now let's see what are the typical steps. The question is, I have to find out the new basis vectors. I have to find out the new basis vector. Once you find the new basis vector, your job is done. Earlier the basis vectors are v1, v2, and vn. Now you are transforming to the u1, u2, and un also, or in some subset is uk, u1, u2, and uk. You are taking some out of this, and you are selecting the subset of basis vectors. Now the question is, how can I get these basis vectors? How can I generate these basis vectors? Okay, let's see in the principal component analysis and what was the idea behind this. Okay, so the idea of this principal component, this u1, u2, u2 generation of u1, u2, uk is, so in the principal component analysis, what they are doing that these new basis vectors are called principal components. These new bases called the principal components, and these new basis vectors are lied in the direction in which there is a maximum data variance is there. Maximum. So in which direction the maximum data variance is there, there I am keeping the first principal component. And the next principal component will be put in which direction there is a maximum data variance will be there. So there in that case, I am keeping the second principal component there. Yes. Of course, all the principal component are orthonormal. Ortho, they are unit size, and of course they are perpendicular to each other. So the question is, how do you find it? The clever idea is, so you can find the eigenvalues of the covariance matrix or eigenvector of the covariance matrix. So first you get the covariance matrix. The covariance matrix, how do you get the covariance matrix? Suppose if you are having n dimensions, so the covariance matrix will be the variance between the all pair of features. So this is the feature one. So the feature one. So what is the variance between the feature 1 to the feature 1? What is the variance between the feature 1 to the feature 2? What is the variance between the feature 1 to the feature 3? And what is the variance between the feature 1? Similarly, for the feature 2 to 1, 2 to 2, and similarly this is n. So it is a matrix of n cross n if the n is the number of dimensions. This is called sigma x. The sigma x is of dimension n cross n. And where what is this ui? Ui is a basis vector, or it's also called a principal component, and this is called lambda into ui. What is mean by that? So for which value you have to multiply, which value, this is a matrix multiplication. So means sigma x dot ui. It's a matrix multiplication. Please pay matrix multiplication. This is a matrix, this is a matrix. It is a scalar and this is in a matrix. So how the scalar is multiplied with the matrix? 2 into 1 comma 3 means the each and every value is multiplied with the same quantity. So 2 into 1 and 2 into 3. This is nothing but 2 comma 6. So the scalar is multiplied each and every value in this vector or matrix, or vector you can also call. That's the scalar to matrix matrix multiplication. So this is a scalar, and so what this is saying that for which value have to multiply so that both will be equal. The sigma x into the covariance matrix and what is called eigenvector. If I multiply that, that value must be equal to the a scalar is multiplied with the eigenvector. So if I want to simplify this, what I have to do? So you have to apply the mod, then it will become, this will convert into a sigma x minus lambda into I is equal to 0. So this, if you solve this equation, you will get the, what is lambda values? Lambda 1, lambda 2 and lambda n. What is this lambda 1, lambda 2 and lambda? These are called eigen. So once you get the eigen values, what you have to do? You have to sort them. So then means lambda 1 is greater than lambda 2 greater than the lambda n. So this is called some lambda 1 dash, lambda 2 dash, means new values, okay? Sorted of lambda dash, lambda n dash. Means you have to perform this sort. The first lambda value is the highest value and the corresponding eigenvector you will have. The second largest value will have second, and like this you will have n eigenvectors. Out of this n eigenvectors, you have to select k topmost eigenvectors, because they already in sorted order, as per the lambda values, you can pick up k topmost eigenvectors as a first k eigenvectors, and you will constitute an eigenvector matrix. You will constitute an eigenmatrix. So this eigenmatrix is called T. What is the T? Where I mentioned T, no? Yes, it's T. What is this T now? Now T is an eigen matrix. So it will have eigenvectors. So this is lambda 1 dash, lambda 2 dash, and then lambda k dash. The dimension is k cross, yeah. If I invert it, okay, or n cross k, whatever, k cross and both n cross k. So you have to transpose it. This way you will get k cross. You see, k cross or n cross both are same. If you transpose, you will get k cross. Means what I mean that there are k features, k eigenvector of size, k eigenvectors of size n. The k eigenvectors of size n. Right. So this T now we got in the PCA. How you got? You find the eigenvectors and arrange them in a sorted order, and corresponding eigenvectors will be the top k topmost eigenvectors, and those two topmost eigenvectors will be considered. But the question is, so what could be the k value? Whether k could be 3 or k could be 4 or k could be 5 or k could be 6. What is the k value? How to decide? We will see now. Yes. So we refer to the same thing. So we refer the largest eigenvectors here as a principal component. So these are the principal components. How you got it? This is an eigenvector, this is an eigenvector, this is an eigenvector, correspond to lambda 1 dash, lambda 2 dash, lambda k dash. This will form the T. Now, so let us do how we have in high level we have explained, and let's see the steps involved in the PCA. Suppose we are given m data points and each of size n. So there are n features and the data is n. There are n features and there is a size of m. This is your data set. So what we are trying to do, we are finding the sample mean. Means we are finding a mean vector x bar. So mean of the first row, mean of the second row, mean of the third column, first column, and like this. You will have a mean vector of dimension 1 cross n. Okay. So 1 row and n columns, or n cross 1 if you transpose it and all. So what we are trying to do, we are finding the x bar, and this is your x. We are finding this x. Now this is the x. So what I am trying to do, once you find this x bar, you are finding the zero mean data. What is mean by zero mean data? So the zero mean data means you are doing normalization. This x bar has to be removed from each and every value in your the x bar. The first in X bar, suppose X bar 1. This X bar 1 will be removed from all the values in the first column, and X bar 2 will be removed from the all the values from the what is called the second column, something like this is called subtraction operation. You are subtracting the corresponding mean of the column from all the column values, So then what you will get the zero mean data. If you find the mean of that particular data after transforming data, the 5 x minus x bar is the 5 data, and this day mean of this is now. Then what we are trying to do, once we make the zero mean data, this is called a normalization. So it's a mandatory step. The reason is that there are different features, the ranges are different and their units are different. The ranges are different, units are different. So to bring the uniformity, what we are trying to do, we are doing the normalization. In the normalization, we are bringing into some specific range. Mostly we will do the this normalization or transformation for bringing the all the data values into the some specific range. So once your data has been transformed or normalized, then you will apply find the covariance matrix. What is sigma x? The dimension of this is n cross n. As per this data, it is an n number of features is the n cross n. So once you find the covariance matrix, then you solve that recurrence, the characteristic equation. What is the characteristic? So what is the value? So sigma x has to be do the matrix multiplication of ui, and this is lambda I into the ui. So when you solve it by, then it is becomes sigma x minus lambda I. Then when you solve it, you will get the how many lambda values? Lambda 1, lambda 2, and the lambda n values. And then you have to sort like lambda 1 dash and a lambda 2 such that is lambda 1. So assume that we are sorted. Okay, after sorting, so the lambda 1 is bigger and lambda 2 and the corresponding. Okay, so then most software packages relates eigenvalues, they are not, if they are not sorted, okay, you can do the explicit sorting. Since these are all not required. Yes. This is more easier. Now, in the step 4, what we are doing? Compute the eigenvalues and eigenvectors of these and sort them. So the sorting, okay. Then the step 5, what we are doing, the very important step is the dimensional reduction step. So what is the dimensional reduction step? So now you got how many eigenvectors? Lambda 1. Suppose they are in sorted order. Lambda 2 and a lambda 3 and a lambda n. So correspondingly, we will have u1, u2, u3, un eigenvectors. These are all called eigenvalues. So you will have eigenvalues and correspondingly you have eigenvectors u1, u2, uk, and up in between. So out of this, I have to find u1, u2, and uk. And because the lambda 1 is the highest eigenvalue, and correspondingly you have a u1. The lambda is the next highest value, then correspondingly you have a u2. So now the question is k topmost. So what is the k value? So that is the k is 3, means out of n features I am selecting only 3 features, because your new transformed space will have 3 basis vectors. It means that each and every sample is represented by 3 components, means the dimensionality of your data is 3. The k is now nothing but your dimensionality. Now, so what is the minimum value of the k? How can I choose this hyperparameter? So is by using what is called information loss. We want to minimize the information loss. Sometimes what percentage of information you want to preserve. So I already mentioned that how much information is being preserved is represented in the form of the variance. So the variance is nothing but the what is called eigenvalues. Eigenvalues. How much variance is preserved is nothing but it's given by the eigenvalues. You know, total variance and variance preserved by top k eigenvalues. It will give the percentage of, it will give the percentage of variance uh, preservation or data preservation, isn't it? Now, this is nothing but the summation of lambda I is equal to 1 to n. The denominator is this. Whatever this is summation of I is equal to 1 to k and lambda. The numerator is talks about the how much variance is preserved by the k eigenvectors, and this denominator talks about how total variance preserved by all the eigenvectors. That's the idea. That's it. Now let's see. I think here I didn't mention. Yeah. Yes, you can see this is whatever I said. So this is the dimensional reduction step that you have to carry out, right? So suppose the t is 0.9, for example, we preserve 90% of information or variance in the data. If k is equal to n, the k is equal to n, what will happen? I ask this question. The k is equal to n, then we preserve 100% of information in the data. That is just a change in the basis. There is no information loss. We are preserving 100% of information. Okay? Now let's see its implementation in the Python. The question is, now you got the t. Now you got the t, right? Now you got the t. What this t has to be do? So means there is x and has to transform with the y with the help of t. This is called some transformative function. How you will get the y? How you will get the y? You have to multiply x with the t is equal to y. Means if you want to get the y, so once you get this x, which is a eigenvectors u1, u2, uk, this has to multiply by what is this x? This is your actual data. The actual data has to multiply with the t to get this y. This is you have to try to remember. Okay, this is the finally we want to achieve, because ultimately we should get y. How you will get the y? But multiplying the t which you obtained just now with the input matrix. So now let's see the interpretation of the PCA, principal component analysis. As I mentioned, so this is your basis vector x1 comma x2 in the original space. So this is my new space. You see here the basis vectors are like this, but here slightly rotated, and there is a movement in origin. Here 0 comma 0, it's called origin. Now origin I moved from here to here. The shift in the origin, and we have shifted the origin and rotated the some degree my basis axis, such that why I am doing all these things, we are transform is shifting of the origin and rotating the axis. Why we are doing so? So we have to align these my principal components. We have to align my principal component such that in which direction I have to keep, so that I can preserve the maximum information. Okay. So the idea is the U1 will be positioned in the direction where the maximum variance will be there, and the next principal component will be shared along the will be projected in the direction where the next maximum variance will be there. Okay, so the U1 direction of the maximum variance, and of course the U1 U2 are orthogonal. Here the input dimension is 2. Obviously, we have only 2 principal components. So the PCA chooses the eigenvectors of the covariance matrix corresponding to the largest eigenvalues. Means you have to sort it. The eigenvalues correspond to the variance of the data along the eigenvector direction. What is this eigenvalue will represent? The corresponds to the how much variance is preserved in the direction of eigenvector. Therefore, the PCA projects the data along the direction where the data varies most. In which direction which data varies most, in that direction we will project this orthogonal, this principal components. The PCA preserves as much as information in the data by preserving the as much as variance in the data. That is, data preservation is nothing but data preserving the variance only. This is one example, so you can go through it. So let's see, there are eight data points 1, 2, 3, 4, 5, 6, 7, and 8. The two dimension means 8 rows, 8 by 2. You have 8 rows and 2 columns, right? Now you will find the covariance matrix. After finding the covariance matrix, the dimension is 2 by 2 because there are two features, the dimension is 2 by 2. Now the covariance matrix is this. Once in the covariance matrix, what you do, sigma x minus lambda I whose depth should be 0. When you solve it, you will get the eigenvectors called lambda 1 and lambda 2. What is the lambda 1 value? So lambda 1, after solving this covariance matrix, character equation, you will get lambda 1 as 9.34 and lambda 2 as 0.41, and so we have to sort it. So lambda 1 is comma lambda 2, so lambda 1 is greater than lambda 2, and you will have eigenvectors. Every lambda value will have corresponding eigenvector. So this is eigenvector. When you substitute eigenvalue in this, you will get the eigenvector. This is eigenvalue corresponding to lambda is equal to 9.34, and this is the lambda value correspond minus much its value 0.41. 0.41. Right. Now it means that this is lambda 1 and lambda 2. Now you got covariance matrix. What is the now? What is the t now? What is the t now? 0.81, 0.49 minus 0.59, 0.81. Yes. Now, for example, I want to preserve. So the next question is, now you got the T. Now where the T is, now you got the matrix tree is equal to eigenvector corresponds to U1 and U2. We got two dimensions. Okay, the value 0.81 something. Now the question is, now we have out of these two features. So I want to know that total variance is 9.34 plus 0.41. And out of this 9.34, how much variance is preserved? How much variance is preserved? By only eigenvector 1, only eigenvector 1 alone. Eigenvector 1, how much is preserving? 9.34 divided by, how much its value? 9.34 plus 0.41, 9.75 divided by 9.75. So this only, yes, the only this one, the eigenvector one is preserving 90% of information. The UT is preserving remaining 5% of information. Means if I am putting the threshold as a 90%, means if you select one feature, the one feature, only one principal component is sufficient, because as alone this itself is more than 95% is preserving the information. Means you can take one feature out of two features. That's the way we are doing the feature selection dimensional reduction step by using this technique. Means here k is equal to 1 only. Right. Okay. And the principal components are dependent on the units used to measure, as I mentioned, and the original values, range of the values. And that's why it's always suggestible to use normalization prior to applying the caprice. And a common normalization is what is called Z-score normalization. You know what you do the Z-score normalization. What is Z-score normalization? The Z-score normalization, you will do the mean will be 0, the mean will be 0, and the variance will be 1. You will means zero mean data and unit variance data. How can you do zero mean data? That we have seen x minus x bar, and if you are right, this if you when you do the subtract x bar from each and every sample, then you will get zero mean data. How do you get unit variance data? By divided by sigma. This is called Z-score normalization. So x minus b by sigma means, so every sample has to be subtracted with this corresponding mean and the corresponding the variance. Then you will get zero mean data. Here, if it is a multi-dimensional, because here mu is a column mu. The sigma is column sigma. So there are multiple columns, right? So this column will have a mu and sigma. This will have mu and sigma. It will have its own mu and sigma. So of course this we will capture in the mu vector or xi bar. and this sigma bar, it's called sigma vector. Okay, in that we will have all these values corresponding. So when you are subtracting xi, the corresponding column mu and column sigma you have to take for the calculation purpose. Okay. Now let us look at its implementation in the Python. So I'm making the Google Colab platform. So where you don't require to install any Python and Anaconda. So in the directly from cloud itself, you can run your Python scripts. Okay. So here I'm. Those who are beginning of the Python, you can directly use the Colab facility, Google Colab facility. So today experiment purpose, I have taken now. So for the experimental purpose, there are two cells. One is the code cell, another text cell. So when you want to write, the code cell is executable. Means if you write, if you want to execute any commands, you have to create the code cell. And if you don't want just simply So for the experiment purpose, I've taken pre-mind and diabetes data set, and it is having 8 features and 768 records. Now, for the PCA purpose, mostly I will require some algebraic for matrix multiplication or a vector multiplication. I required some functions which are related to the matrix multiplication and all. So that's why I'm importing the NumPy library function. And of course, for data processing, because if I want to access some Excel sheets or if I want to read the data from the CSV file and all, so I require some data processing functions that I can. For that, I require Pandas library. So I'm importing Pandas. And for plotting purpose to visualization purpose, I'm using MATLAB lib library function, and that's it. With that, I'm importing all the library functions required for my PCA analysis. So I'm executing those commands. Yes, it is. Yes. So when there is a tick mark, means it's completed. The stream is executed successfully. Now, and what I'm doing next, I'm trying to load the data set. And for that loading data set, what I'm trying to do, so as the Google Colab is there in the, I'm executing from the where I'm, so in my Google Drive. Okay. So what, first of all, I have to import my data to the library from my local host, my computer to the what is called the Google Drive. So that I'm doing, I'm choosing a file, the diabetes. So I'm loading my file to the Google Drive. Yes, please. My Google Drive is successfully loaded. Now from the Google Drive, I am accessing into the data frame called DF. So For that, I am using pandas read underscore CSV. So there I am using pandas library functions for sorry. Yes. Now, once from the Google Drive, I'm storing into my data frames. Once I store in my data frame, let me try to display the contents in my data frame. So my data frame is now loaded with the data set. It is having 9 features. Last is a class table, supervised information or growth information, and it has 768 records. Let me display its dimensionality also. Taking some time, please. Yes, this is a data set. Now, this is not required. So let's see the shape of my data set means it has 768 records and 9 columns. So for extra implementation purpose, what I'm trying to PCA, you don't require the class label. So that's the reason I am segregating, I'm separating the class label into the white list and putting all the feature into the X. Now X is containing only, just I'm simply putting the X. The X will contain information without the class label. So if you want to check, you can check with the numpy.shape there. Where instead of 768 cos 9, it is now 768 8 only. Now, as I said, for the PCA, standard, what is called normalization is required. Normalization is required. We are doing the standard normalization by using inbuilt library functions called standard scalar dot fit underscore transform. So with this help, we are doing this transforming my data into zero mean and unit variance data using Z score normalization. So this is my transformer data. So X underscore standardization means the transformer data. So of course the dimension of this is the same as the original data. The original data is 768 plus 8 and X underscore standard is also 768 plus 8. Now the next step is once you can transform the data and normalize the data, you have to create the covariance matrix. So in that what is called NumPy, you will already having inbuilt library function for creating the covariance matrix. So by using this function, I am calculating the covariance underscore my underscore mat. This will store my covariance matrix. And if you this is my covariance matrix. You see the dimension of this covariance matrix is how much? Can anybody say what is the dimension of this covariance matrix? 8 by 8 because there are 8 features 1, 2, 3, 4, 5, 6, 7 and 8. 8 columns and 8 rows. 1, 2, 3, 4, 5, 6, 7 and 8. So it's 8 cross 8. Now once we get this, then what I'm trying to do that, I want to so the same, the covariance matrix, the covariance of the individual, what is called self features will be maximum 1 and remaining all are in between 0 and 1 minus some other values. So once we are this have same information I kept in this what is called in a table matrix form. Now next, once we get the covariance matrix, you have to find the eigenvalues and eigenvectors. So for this you will have a np dot linear algebra dot li linear algebra dot eigi. By providing input as a covariance matrix, you will get the eigenvalues and eigenvectors. If you see the eigenvalues over here, they are not in sorted. Okay, you have to sort it. Okay, so they are not in sorted. You have to sort it, and so once you saw, now the eigenvalues are sorted in a descending order. Once you cite it, you have to find the total variance of all these. What is the what is the variance preserved by each and every principal components? If you see in the zeroth principle, fixed principle component is preserving the 25% of variance of total. In the second principal component is where nearly 22% of total variance, and like third principal component nearly 15%. Fourth also, and fourth also is nearly 12%, and the fourth is nearly 10, and the fifth and fifth also nearly 10%, and 6 and 7 and principal components are nearly 5% of towards the total variance contribution. So means the maximum variance is preserved by first two, three, first four up to first 5 to 6 principal components. Suppose if I want to achieve the 90% of information preservation, so you have to consider the top 6 feature, top 6 principal components, that is your top 6 eigenvectors. Okay, now so for simplicity purpose, I have considered only top 2 eigenvectors because I want to preserve only 50% of information. 50% of information. So those two principal components are these. So now I am created matrix W. This is nothing but this T. So once you create this matrix T, now you are multiplying with the matrix T with the input transformed matrix called X underscore T. So this is your new transformed matrix. So as I said, once you get the T matrix, this T matrix has to multiply with the input matrix. What is the input matrix? X underscore STD. You have to do the dot product. This is your Y. You got transformed data. If you see the first feature value here is minus 1.06. Here in the first feature value is, what is the first feature value? 6. See, the 6 has been transformed to the minus 1.06. They both are not same. It's a transformed data, and how we are transformed by using eigenvectors and all. Okay, this is how we carried out the principal components and how we have transformed the data from one set of access to the another set of access by changing the what is called by changing the shifting the centroid and rotating the axis, we are transforming your data. Okay, this is the idea behind the principal component analysis. So if you have any doubts, please let me know. So now the questions, 20 minutes time is there. If you have any queries, please let me know. Nice. Yes. Yes. Hello. Yes. Any doubts? If you don't have any doubts, I'm closing my session. Okay. Thank you. Bye.
Thank you, sir.